Hello everyone, I hope everybody is fine and ready to watch another lecture on limit computations. So this is the 12th technique of limit calculation I'm talking about, 12 and number 13. We have already discussed 11 um, techniques in the past, and this number 12 is called oscillating limits, okay? And the reason why it's called oscillating limits is because sometimes the functions they fluctuate between two values, just like sine function, cosine function, and they keep oscillating and oscillating. And it's hard to find actually an answer for the limit. Look at this function. It says 2 times sine of 1 over x. Okay, if you use some sort of graphing software and you draw the graph of this function, it's going to look like something like this. It would be like a sinusoidal function on the right side and on the left side. And then as you approach a zero from left side or right side, the periods of these cycles become like smaller and smaller and smaller. And the graph oscillates very fast, at a neighborhood of the origin. And that too doesn't play an important role here. Like it could be like 5, it could be whatever. But sine of 1 over x, end of the day, itself is fluctuating between two values, 1 and negative 1. Now, if you multiply it by 2, it's going to be fluctuating between 2 and negative 2, obviously. But the thing is that if x approaches 0, then 1 over x approaches infinity. So that means that we're finding the sine of a very, very large angle. But it doesn't matter how large the angle is, because this sine value is going to be, after all, something between 1 and negative 1. And as I said, the graph keeps fluctuating or oscillating, between the two max mean values. And to tell you the truth, it is very difficult to say what the limit will be. Could it be like 0.5? Could it be negative 0.5? Could it be like 0.9? Could it be negative 0.6? Or could it be actually 0 itself? We don't know. We don't know that because of the oscillating nature of the function at a neighborhood of the origin where x approaches 0. We want to find the limit of 2 times sine of 1 over x when x approaches 0, and we see that we do not end up with a fixed final answer that we say, okay, that is the limit. So, making a long story short, these kind of oscillating situations, because we don't know what the answer is, we know that it has to be between 1 and negative 1. That is a fact. So I can even write down here that sine of 1 over x, or sine of actually anything, any angle is always between 1 and negative 1. But the thing is that when x approaches 0, sine of 1 over x is like oscillating between these two values, and we don't know what the exact value is. Therefore, we're going to say that this limit does not exist. But the reason why we say so is not because the value of the function approaches infinity. It's not like the value of the function explodes to a huge, huge number. Or it's not even because of left-hand limit not being equal to right-hand limit. These were the reasons we had in the past where we said limit doesn't exist. But this is like a third case scenario here, and we call them oscillating limits, and limit does not exist. The other type, I call them comparative limits, okay? So limits of functions like this, like the numerator is exponential, the denominator is a quadratic function. Here we have a numerator logarithmic function, the denominator is a linear function. Here we have a combination of both. Here we have a cubic function at the top, logarithmic function at the bottom. So they're not that easy. They're not that easy to find. Limits of these functions are not like straightforward. But by this method I'm going to suggest, perhaps you will be able to find out what these limits are. Consider just x for now, and I have selected different values for x, like 1, 10, 1,000, and 1,000,000, just for example. And consider some other functions, like x squared, x cubed. These are quadratic cubic functions. Exponential function 2 to the x, e to the x. You know that e is 2.718281. approximately. It's an irrational number. And then x to the exponent of x, which is like a little bit weird. Ln of x, which is natural logarithm of x, common logarithm of x, and 1 over x, which is the reciprocal function. So if I select x equals 1, okay, then what would be 1 over 1? The reciprocal function would be just 1 over 1. The value of 1 over x would be 1. But log of 1 is 0, and so is ln of 1. X squared and x cubed both will be 1, because 1 squared is 1. 2 to the exponent of 1 would be just 2. And e to the x would be 2.7182, and then 81, and so on and so forth. And x to the power of x will be 1 to the power 1, which is 1. So this is what we will end up with if x is equal to 1. And we can simply sit down and just compare these values. Now the question is, what happens if x becomes 10, for example? If x is 10, then 1 over 10 would be 0.1. And then log of 10 is clearly 1 itself, because this is the common logarithm. Natural logarithm of 10 is 2.3025 if you use a calculator. That's what you will end up with. And 10 squared would be 100 squared, which is, x squared would be 10 squared, which is 100. And then x cubed would be 10 cubed, which is 1,000. Okay. And then we have 2 to the exponent of 10, which is 1,024. And e to the exponent of 10 using a calculator is 22,000. So 22,000 and 26.5 according to my calculator. And 10 to the exponent of 10 is, of course, an extremely large number. What happens if x becomes even larger than 10? What if x is 1,000, for example? In that case, x squared would be 1,000 squared, which would be 1,000,000. Or you can say 10 to the exponent of 6. X cubed would be 10 to the exponent of 9. And then 2 to the exponent of 1,000. If you're using calculator, you will see that your calculator does not have the power to find this huge answer. So you get something like overflow error message. That's what we get, overflow message, because the number is like extremely large that it doesn't fit in your calculator. Your memory of calculator is not enough. And if x is 1,000, 1 over 1,000 would be 0.001. And then log of 1,000 would be 3, obviously, because the base is 10. And then ln of 1,000 is 6.907, for instance. And if the value of x in the middle column becomes even larger, we have 1,000,000, for example, then x squared would be 10 to the 6 squared, which is 10 to the power of 12. Next one will be 10 to the exponent of 18. And sure enough, we still get the overflow error message on the screen of the calculator, because the values of those functions, exponential functions, is like so large that it doesn't fit in your calculator. Then you find the natural logarithm of 1,000,000. It's going to be 13.815. And then this one is common logarithm of 1,000,000, which is 6. And then 0.000, and then 001. So there's 5 zeros there, and then 1. So that's the value of 1 over x. So why did we construct this chart? I'll tell you why. Because we wanted to compare the behavior of these different functions when x becomes very, very large. Of course, 1,000,000 is large, but it's not that large. You know, we have like billions of billions, you know. And when you talk about infinity, that's, unimaginably large. So here, if x increases, we see that x squared increases much faster, and x cubed increases even faster, and the exponential functions and those other functions are increasing like extremely fast, and they become very, very large that you can't even, show it on the screen of a calculator. On the other hand, when you compare the natural logarithm with the common logarithm, you see that when x increases, the natural logarithm increases faster, because See, 13.8 compared to 6, obviously, natural logarithm increases faster. And 1 over x is the reciprocal function, and we see what happens if x increases, then 1 over x decreases, to a very, very, very small number. So if x approaches infinity, basically 1 over x would approach 0, something that we already knew about it. So this one, it says, what is the limit of 4 times ln of x divided by 2x minus 1 when x approaches positive infinity? The numerator is a logarithmic function. We saw what the behavior of natural logarithm function is when x increases and approaches positive infinity, and the linear function is 2x minus 1. So when x approaches infinity, then 2 times x also approaches infinity, and if you subtract 1 or add 1 to that huge value, it doesn't matter, of course. So we can compare with the linear function. So the numerator is logarithmic, the denominator is linear, and x is increasing, okay? X approaches positive infinity. Now, which one of these two functions in the numerator or denominator do you think will approach infinity faster? Because separately, if you look at the numerator itself, sure, numerator approaches infinity. Denominator by itself approaches infinity. But which one approaches infinity faster? If x is like only 1 million, ln of x is only 13.8, not even close, right? So we see that the denominator approaches infinity way faster compared to the logarithmic function in the denominator. That means in long run, when x approaches positive infinity, the denominator becomes way larger than the numerator. And that means that the whole fraction becomes smaller, approaching 0. Therefore, the answer to the limit is 0. Next one, it says, what is this limit? So 2 times x times 3 to the exponent of x plus 1. The numerator is only 3, or it's just a fixed number. So if the numerator is a fixed number and x approaches positive infinity, this whole denominator approaches infinity like way fast, and 3 divided by that extremely large number would be an extremely small number. Therefore, the limit is 0. In the next question, we have 2x cubed in the numerator, 1 plus log x in the denominator. So you see that the numerator has a cubic function nature. The denominator has a logarithmic function nature. So this column, log x, and x cubed over there compare. If x increases, we saw what happened when x was increasing from 1 to 10, 10 to 1,000, 1,000 to 1,000,000. We saw what happened to the logarithmic function. It went up by like 1 and then 3 and then 6. But then x cubed already reached 10 to the exponent of 18, which is like drastically huge number. So if I ask you which one of these two, numerator or the denominator, would approach infinity faster if x approaches positive infinity, obviously you're going to say the numerator will approach infinity much faster. Therefore, the numerator becomes extremely large, and that means that the limit is going to be positive infinity, or in other words, there is no limit, and the limit does not exist, we can say. Next one, exponential function in the top, quadratic in the bottom. So this column and that column, we can easily compare them. And we said earlier that 1 plus x squared or like 2 plus x squared, it doesn't matter. Imagine like you have $1 billion in your account and you give me $1, for example. I call you still a billionaire. I'm not going to say you are billionaire minus $1 kind of person. You're still a billionaire. Or even if I give you $1, I'm not going to say you are a billionaire plus $1 person. No, you're still a billionaire. So it doesn't matter to you if you lose $1 or if you just gain $1. Do you understand what I'm saying? So here, if you have just x squared, or even have 100 plus x squared, it doesn't matter, because infinity is like so large that 100 or 1 added, subtracted, it doesn't make any difference. So a billionaire person is so rich that $1, $10 here and there, it doesn't even matter. Okay, so the numerator is exponential, the denominator is quadratic. When you compare them, you can tell me if the numerator approaches infinity faster or the denominator. Obviously, the answer is going to be, of course, limit does not exist, because it's going to be positive infinity. Now, mind you, if I would write this upside down, if I would write limit of x squared plus 1 in the numerator, and then e to the x in the denominator. Okay, then in this case, the denominator would approach infinity much faster compared to the numerator. Speaking of comparative limits, that was a good title I selected, I guess. Comparative limits. So comparing the denominator to the numerator explodes and becomes way larger when x approaches positive infinity compared to the numerator. Therefore, the limit would be 0 in this case, for instance. Okay, so I hope you understood these kind of weird limits and you learned how to find the limits by comparison. And also you learned about the oscillating limits, number 12 and 13 of limit computation we have started discussing in this course. Thank you for your attention and keep practicing.